The gunnery system of the Boeing B-29 Superfortress marked a groundbreaking development in the history of heavy bomber defense, representing a shift in how aerial warfare was conducted. Beginning production in July 1943, the B-29 became a critical asset for the United States during World War II, answering the military's urgent need for a long-range, high-altitude strategic bomber. Originally conceived in 1938, the B-29 was designed to surpass earlier bombers in every measurable category: speed, range, and bomb load capacity. Unlike its predecessors, the B-29 was specifically tailored for operations in the Pacific Theater, where vast distances between islands and enemy targets demanded extraordinary reach and endurance. The B-29 could fly at altitudes up to 36,000 feet, carry a bomb load of up to 20,000 pounds, and had a cruising speed of around 230 miles per hour. At its peak, the aircraft could reach a maximum speed of approximately 350 miles per hour. With a loaded range of nearly 4,000 miles, its operational capacity was unparalleled at the time. This technological superiority influenced American strategic planning in the Pacific. With the Marshall, Gilbert, and Solomon Islands already under U.S. control, military planners focused on seizing the Marianas, specifically Saipan, Tinian, and Guam, because the B-29 could strike directly at Japan from these locations, even though they were over 1,500 miles away. The bomber's extended range gave the United States a unique advantage, fundamentally shaping its approach to the war in the Pacific. Beyond its raw performance, the B-29 brought a suite of technological advancements that elevated it far above previous bombers. One of the most important was its pressurized and heated crew cabin, which significantly improved comfort and allowed the crew to remain alert during long, high-altitude missions. This feature allowed the aircraft to fly above the effective range of most enemy fighters, giving it an additional layer of safety. The B-29 also introduced a two-wheel tricycle landing gear configuration, a major improvement over earlier bombers like the B-17, which had a tail wheel, and the B-24, which had a notoriously unstable single nose wheel. This innovation made landings safer and more reliable. But perhaps the most remarkable advancement in the B-29 was its centralized fire control system, which transformed defensive gunnery from a scattered and inefficient system into a coordinated, highly effective network. Developed by General Electric, the system, known officially as the Type 2 CFR-55B1 Central Fire Control CFC system, was a marvel of engineering. It included 5 remote-controlled turrets, 5 gun sights, 5 computing gun sights, and an electrically operated switching system. Each turret could be aimed and fired by a gunner stationed at a remote sighting station, and each of these stations was connected to a computing gun sight that automatically calculated firing solutions. This meant that gunners could control more than one turret if needed, and that multiple turrets could be directed at the same target to maximize firepower. The B-29's 5 turrets were strategically located to provide all-around coverage. 2 turrets, one on top and one underneath, were situated forward of the aircraft's center, just behind the pressurized crew compartment where the pilot, co-pilot, navigator, and flight engineer were stationed. 2 more turrets, also one top and one bottom, were placed at the rear of the aircraft, ahead of the tail fin. The 5th turret was mounted in the tail itself, aimed to the rear. A crew of 11 operated the B-29, with 5 of them serving as gunners. Each had a specific role and area of responsibility. The side gunners, known as blister gunners, operated from bubble-shaped windows on each side of the fuselage. The bombardier also doubled as the nose gunner when not directing the bomb run, and he operated from a forward-facing position at the front of the aircraft. The fire control officer, sometimes called the top gunner or ring gunner, sat centrally in the aircraft in an elevated position referred to as the barber chair, overseeing the coordination of the entire defensive system. The tail gunner was the only person seated in the rear pressurized compartment, Each turret had a designated primary gunner who was given first priority in controlling it. Through a series of switches, other gunners could assume control of turrets when needed. For example, the nose gunner typically controlled both forward turrets, but one of the side gunners could take over the lower forward turret if required. The top gunner held secondary control over the upper forward turret and was primarily responsible for the upper rear turret. The side gunners had overlapping responsibilities, including coverage of the lower rear turret and support for the tail turret when necessary. Despite the complexity, this overlapping system allowed for flexibility and redundancy, increasing the aircraft's ability to defend itself from attacks from any angle. To prevent friendly fire or accidental damage to the B-29 itself, each turret was equipped with fire interrupter cams, which physically prevented the guns, except for the tail-mounted ones, from firing into the plane's own wings or tail section. However, there was still a risk of firing into friendly aircraft flying in formation if turrets were being reassigned between gunners and pointed momentarily at the wrong target. Each of the 5 turrets typically contained 2 air-cooled Browning M 2.50 caliber machine guns. Later versions of the aircraft added 2 more 50 caliber guns to the upper forward turret in response to the increasing threat of frontal assaults by enemy fighters. To manage heat buildup and avoid damage to the barrels, gunners were instructed to fire in short bursts and allow at least a 3-second cooling period between bursts. In some instances, they could fire up to 25 rounds in rapid succession, but the heat generated could cause the barrels to expand dangerously, potentially resulting in an unintended discharge or even catastrophic failure. Because of this, a mandatory cooling period of 15 seconds was required after extended firing, which could feel like a very long time when under attack. Early versions of the B-29 were also equipped with a 20mm cannon mounted in the tail. This cannon couldn't be fired independently, but worked in tandem with the tail-mounted .50 caliber machine guns. It was integrated into the same sighting and fire control system. Although the .50 caliber round was heavier than the 20mm shell, the cannon offered greater firepower, making it an effective supplement. Each gunner operated a sighting system that included a small manually adjusted gun sight with a 2x3-inch glass lens. These sights were electrically connected to the CFC system and allowed gunners to see and track targets, even in low light conditions, using movable sky filters integrated into the optics. All of these elements combined to make the B-29 Superfortress the most technologically advanced bomber of its time. Its design not only improved the safety and effectiveness of long-range bombing missions, but also introduced a new era of aerial warfare, where centralized fire control and crew comfort were as vital to mission success as speed and payload. The B-29's legacy lived on long after World War II, not just because of its combat record, but because it redefined what a strategic bomber could be. The gunner's task involved detecting an enemy aircraft even if it was attacking from behind the sun. A circular pattern of dots known as a reticle, similar to the crosshairs seen in rifle scopes or the focus indicators in camera viewfinders, was reflected onto the optical glass through a reticle lamp that could be adjusted for brightness. Before making any adjustments to the target size knob, which could be rotated to display wingspans ranging from 35 to 150 feet, the gunner first had to visually identify what type of enemy aircraft was approaching. Turning this knob would change the projected reticle size and display the current target size setting at the topmost part of the reticle, allowing the gunner to align it with the enemy aircraft's wingspan. Once the enemy plane was identified and the reticle adjusted, the gunner would align the central dot of the reticle with the center of the target aircraft. Then, by adjusting the range wheel, the gunner ensured the wings of the enemy plane matched the size of the reticle circle. Tracking the enemy required smooth and precise motion of the gun sight both vertically and horizontally, ensuring that the target stayed centered and within the proper range. To do this, the gunner rotated two hand wheel grips on the sides of the gun sight. These controlled vertical adjustments, while turning the entire gun sight along the gunner's torso, corrected horizontal alignment. Friction adjustments on the sight allowed the gunner to fine-tune how easily the sight moved, adapting it to their preference for better control. Every movement made with the gun sight, whether up, down, or sideways, would cause the turrets and cannons to respond electrically through a coordinated system. This technology included amplifying generators that powered the motors responsible for aiming the cannons, as well as servo amplifiers and Selson generators placed both at the gun emplacement and the gun sight. With the exception of the tail mount, the guns could tilt up to a full 90-degree angle relative to the aircraft's body, and the turrets could rotate a complete 360 degrees for all-around defense. Instead of using traditional firing triggers, the gunner used thumb-operated buttons located next to the hand wheels. To activate control over the sighting station, the gunner had to press the hand wheel with his left palm, engaging a special action switch. This switch not only enabled firing, but also served as a fail-safe. If the gunner became incapacitated and let go, that sighting station would automatically stop controlling the guns. In such a case, control was handed off to another sighting station, keeping the aircraft's defensive system operational and capable of responding to threats. Once the enemy was properly tracked and aligned, the gunner would fire when the target entered effective range. At this point, the Central Fire Control CFC system took over the aiming. It moved the cannons automatically and relied on a computer that constantly performed real-time calculations to ensure each bullet had the best possible chance of hitting the moving target. With computer-assisted aiming, the guns had an effective firing range of around 900 yards, more than twice the distance of most enemy fighters' weapons and 50% greater than manually aimed guns. This accuracy was achieved through a system that transmitted synchronized movements between the gun sight and the weapon using Selson mechanisms. The computer introduced necessary corrections for bullet trajectory by factoring in several dynamic conditions. These included the lead required to hit a moving aircraft, parallax due to the physical distance between the guns and the gun sight, and ballistic compensation to account for gravity and wind. Since the guns were mounted at different points along the aircraft's body, the computer had to consider parallax error, the difference in perspective between the sight and the guns. For targets moving at speeds near 250 miles per hour, the deflection caused by gravity and air resistance was significant. The computer automatically accounted for these variables, calculating how far the bullet would drift and correcting for it even before the trigger was pressed. Inputs necessary for these calculations came from various sources. The gunner provided range data through the range wheel and aligned the sight for elevation and azimuth. The navigator supplied additional information like the aircraft's altitude, true airspeed, and outside temperature, all of which affected air density and, in turn, bullet drag. Two gyroscopes mounted on the gun sight helped determine the relative speed and direction of the enemy aircraft, adding crucial data to the calculation. Different types of computers were used depending on the layout of the turrets. A single parallax computer, such as the General Electric Model 2CH1C1, was used for stations where the gun sight controlled one set of guns directly ahead or behind, like the nose or tail turrets. More complex double parallax computers, such as the Model 2 CH1D1, were used for side or top gunners who controlled multiple turrets placed at varying distances. Though only two turrets could be operated simultaneously, control switching mechanisms allowed these gunners to access up to 3 different ones as needed. The fire control computer itself performed all its calculations mechanically, despite receiving all its input signals electrically. This was necessary because electronic computing at the time was impractical due to the high power requirements and heat output of vacuum tubes. Mechanical systems, while large and heavy, were more reliable in an aircraft environment. The CFC computer was about the size of a suitcase and weighed more than 50 pounds. Containing a network of interconnected computing modules. Electrical signals from the aircraft were converted into mechanical inputs through Selson devices and potentiometers. One major component inside the computer was the ballistic calculator. It had built-in data about gravity's effect on the bullets, the muzzle velocity of rounds fired from the .50 caliber Browning M2 machine guns, and other ballistic properties. This unit required information about the aircraft's altitude and air temperature to calculate drag, as well as gun position and target range to determine the initial trajectory. It even factored in the aircraft's speed to make wind corrections. All of these inputs combined to help the gunner hit fast-moving enemy planes with deadly accuracy while flying at high altitudes in combat. The Parallax computing unit in the B-29 Superfortress was designed to account for the distance between the gun sight and the turrets it controlled. In order to calculate the necessary parallax correction, the system required accurate knowledge of both the target's range and the gun's location at any given moment. This correction was determined using trigonometric methods. The relative velocity of the target, its range, and the ballistic characteristics of the weapon, all of which influenced the time it would take for a projectile to reach the target, were processed by a calculating unit. This data was then used to determine the lead correction necessary for a successful hit. The output from the computer, which came as a parallel signal from the gun sight modified by the sum of the three corrections, parallax, range, and lead, was sent to a servo amplifier, also known as the feedback controller. This amplifier then powered two motors responsible for adjusting the gun's position, one for elevation and the other for azimuth. As a result, the gun and turret were moved to a corrected position, which differed slightly from the one directly aligned with the gun sight. Because the system was electrically linked, it did not require the computer to be physically close to the gun sight or the turret. The computer used for the nose gunner was placed in the forward pressurized cabin behind the pilot's armor. The other four computers were positioned under the floor in the radar operator's compartment toward the rear of the middle pressurized cabin, surrounded by armor for protection. If a malfunction or combat damage rendered the computer system inoperative, a manual override feature was available. This feature allowed the gunner to operate the cannons using a flip-down peep sight without computer assistance. According to the U.S. Army Air Forces, a total of 3,760 production B-29 Superfortresses were delivered during the war. Boeing built about 70% of them at its plants in Renton, Washington, and Wichita, Kansas. The remaining bombers were produced by the Glenn L. Martin Company in Omaha, Nebraska, which later became part of Martin Marietta, and the Bell Aircraft Company in Marietta, Georgia. Once construction of the aircraft was completed, the targeting computers and weapon systems underwent thorough testing before the aircraft could be declared battle-ready. Bore sighting equipment was used to adjust each gun and turret to align with designated target marks. Following this, each turret was matched to the viewing station that would control it, using a pre-established harmonization target placed at least 100 feet away from the aircraft. Modifications were made to the Selson unit at either the sighting station or the turret, depending on the configuration of the gun sight and turret. The entire targeting system, including input systems and calculation components, was tested with an advanced device equipped with over 50 dials, meters, and switches. As aircraft production began to outpace the manufacturer's ability to install the Central Fire Control CFC systems, the U.S. Army Air Forces responded by training their own personnel to handle the installations. Corporal Robert W. Bob Truxell of Lansing, Michigan, was one of the first to complete the B-29 CFC and computer training program at Lowry Field in Denver, Colorado. Truxell had originally trained as an air cadet pilot, but had to leave the program due to a 3-month illness caused by rheumatic fever. The setback proved to be a blessing in disguise, as most of his former unit was killed during a devastating raid on oil refineries in Ploiești, Romania, on August 1, 1943. After recovering, Truxell was reassigned to aircraft armament training and became a turret mechanic specializing in remote control systems. His knowledge of trigonometry, which he began studying during his engineering coursework at the General Motors Institute in Flint, Michigan, helped him excel. He was selected for the B-29 CFC Specialist course in February 1943. Upon completing his training, he received a promotion to sergeant and was given command of the first graduating class of CFC specialists. The team's first assignment took them to Georgia, where they had to navigate the aircraft's pressurized tunnels to access the necessary sections. Truxell recalled using a fire extinguisher to clear civilians who were sleeping in the aircraft tunnels, which had been assembled at government expense. At the Bell Aircraft B-29 factory in Marietta, Georgia, the team worked on a mile-long lineup of completed bombers, aligning their gun turrets and central computers for combat readiness. Once the backlog of aircraft at the Georgia factory had been addressed, aside from a final gunnery system upgrade, the team moved on to various U.S. air bases where B-29 squadrons were preparing for overseas deployment. After each squadron was cleared for deployment, the team would relocate to the next base in need. Truxell described the work as relatively safe and quite fascinating. However, for Japanese fighter pilots, facing the B-29's advanced gunnery system was anything but safe or routine. According to the Army Air Force's Statistical Digest, released in December 1945, during more than 31,000 combat sorties flown in the 13 months from August 1944 to the end of the war in August 1945, B-29 bombers destroyed 9,914 enemy aircraft while losing only 72 of their own to enemy fighters. This account of the B-29's advanced targeting and gunnery systems has been made possible thanks to the efforts of Gregory A. Henry of Chattanooga, Tennessee, who is contributing to World War II history for the first time. His work was supported by the B-29/B-24 Squadron of the Commemorative Air Force in Fort Worth, Texas, and by Dave Santos of the New England Air Museum in Windsor Locks, Connecticut.